Okay. Average rate of change and instantaneous rate of change. Rate of change is going to be vital that you understand it. Basically, that's the big concept in this class is rate of change. How fast, how slow, or if something is not having a rate of change, zero rate of change, is vital that you understand that. There are two types of rate of change that we talk about in this class. There's the average rate of change, all right? There's the instantaneous rate of change, and then the graphical sort of interpretation of them is slope of functions, all right? And they go hand in hand. Slope is the rate of change, all right? Slope is the rate of change. All right, so average rate of change first, because we actually can't do instantaneous rate of change until we get to the really big calc topic. All right, so right now, average rate of change, which average rate of change is something you should have seen in an algebra class somewhere. Whenever they did the distance equals rate times time, that rate was average rate of change. Right. And then we'll talk about the difference quotient, because difference quotient is going to play an important role when we get to the big theorem in the next section. And just practice solving that algebraically. All right, so again, you must understand rate of change of a function, which graphically is represented by the slope of the function. That is a key element to this class. You have to understand what rate of change is. You have to understand that it relates to the slope of the function. All right, so two types of rate of change, average rate of change and instantaneous rate of change. One of them you've done in an algebra class, the first one, average, which is what we're going to be talking about in this section. One of them you can't do until you get to calculus, which we're going to spend the vast majority of this class on the second one, instantaneous rate of change. All right, but you can't get to instantaneous rate of change until we get to some major calc theorems. All right, average first, the one we can do. All right, so again, just kind of understanding the difference between the two. Suppose that you went on a trip and you traveled 200 miles total, and it took you exactly 4 hours to travel those 200 miles. Your average rate of change, your average speed, and sometimes I'll be using speed, velocity, again they mean your average rate of change. Well, your average rate of change is the change in distance over the change in time. That's what it is. Change in distance traveled divided by the change in time. And then you'll see that that's a slope, right? Slope is a change in y over a change in x. Well, y happens to represent distance, x happens to represent time. And so it is a slope. It is a speed is a slope. Well, our change in distance, we traveled 200 miles in 4 hours. The change in time, right, was hours. 4 of them took us 4 hours to do that. And then you do the division. You take your 200 divided by 4, and it comes out 50 miles per hour. And that's important. Miles per hour is the units, and you have to do units on this. Whenever you're doing a rate of change, something should be changing per a unit of something else. So in this case, you're traveling a distance of 50 miles every hour on average. Again, it is on average for those 4 hours. Now, it doesn't mean you're going 50 miles per hour every moment during those 4 hours of that trip or every mile, but that's your average. Sometimes you'll be traveling faster than that. Sometimes you'll be traveling slower than that. If you could add up all of your times and all of your speeds and find the average, your average would be 50 miles per hour. So that's what you averaged. All right, so that's the average. Over the 200 miles, your average speed was 50. Now, sometimes you might have been going 50, but more than likely you were going faster than that and slower than that, and it averaged out to 50. All right, so that's the average rate of change. That's when you do the distance equals rate times time, that's that rate, right? Because we found it by taking distance over time equals average rate of change. All right, that's something that you do in an algebra class. What we're going to get to eventually in this class is the second type of rate of change, which is instantaneous rate of change, which is easy to understand, hard to find, and hard to exactly give a definition for, because there's a bit of a paradox to it. All right, so suppose that 1 hour into your 4 hour drive, you look down at your speedometer and you see that you are traveling at 62 miles per hour, which is higher than your average. At that moment, you look down at that speed, at that instant, all right, that's your rate of change. That's your miles per hour. Now, you look down 2 minutes later, you might be going faster than that or slower than that, just depending on how steady you are with your pedals. But this is your instant rate of change, and it is a different measure than your average, and it's a harder measure. It's easy to understand. I know that every moment I have a specific speed. If I'm walking across the room, I have a speed at every moment that I'm stepping across the room. Even when I stop, I have a speed of 0, right? So every moment I have a speed, I have a rate of change. Finding, interpreting, and defining instant rate of change is actually challenging. It's been challenged physicists and mathematicians for many, many years until Sir Isaac Newton and Leibniz came around and discovered and created calculus in order to solve this problem. Right? Calculus was created because they knew instant velocity existed and they want to be able to find it. All right, so again, we'll get to the instantaneous rate of change more in the later sections. Right now we're going to talk about average rate of change because that's the one we can do with algebra, and we actually need it in order to solve for instantaneous rate of change. They go together in order to do it. All right, average rate of change of the function. The average rate of change of the function with respect to x is when x changes from one point to another point. So average rate of change always has 2 points, at least 2 points. I'm going from point A to point B, or point 1 to point 2. Right, it's the ratio of the change in my function from that point 1 to point 2 divided by the change in the x value from point 1 to point 2. It's a slope. It's the change in my function over the change in the x. The change in y over the change in x, right? This would be the change in the function, which is the y values, divided by the change in x. Ergo, it is a slope. All right, so what it means is this finds how fast or slow, right? It could be a slow. That's what rate means, how fast or slow your speed. How fast or slow the function is either increasing if it's a positive number or decreasing if it's a negative number on average from the first moment to the second moment. So from the first x value to the second x value. Graphically, again, if you look here, change in y over change in x, it is a slope. Graphically, it's the slope of the secant line to my function. All right, my function, non-linear functions specifically, have different slopes on the function. So here's, suppose this is like a cubic function. All right. Any moment on this curve, I would have a different speed and direction. That's what slope is, right? These would have positive rates of change. These would have negative slopes. Over here, I'd have positive slopes again. And so it changes, right? Unlike lines where it's constant slope, these types of functions have different slopes depending on where I'm at. Some of them are positive, some of them are negative, some of them are bigger than others, some of them are smaller than others. And so what we do when we find average rate of change, I pick a starting point. So suppose this is my starting point, that's x1. And I pose this is x2, my second point. All right, so I go up and I hit my curve. There's the first point on my curve. There's the second point on my curve. All right, and I connect the dots using a line. All right, because again, we usually use lines to find slopes. That's my secant line. All right, secant line means it intersects the function at least twice. So this would be the point x1, f of x1. This would be the point x2, f of x2. And then the slope of that line equals the average rate of change of f of x from x1 to x2. So I can look at it and I can see just based on my graph is that it's a very small slope, but it's positive. All right, so it should be moving in a positive direction. So it is this. slope would be I'd find my y values, take their difference, divided by my x values, take their difference. And just based on my graph, I could tell, on average, this function from point 1 to point 2 is increasing, on average, slowly. Not very fast. It's not a very steep line. And actually, if you look at it here it actually decreased a little bit. All right, then somewhere here it hit 0. And then up here it would start to increase and get steeper and steeper and steeper and so bigger. And so this is just an average. All right, this would be taking some of my negative slopes, my positive slopes, averaging them out to whatever that value is. Whatever that, again, it looks like a fairly small slope. All right, that's what the average rate of change is. All right, now we'll stop the video there to kind of get you to understand what the average rate of change is. In the next video, I'm going to introduce the difference quotient, which is just an algebraic way to simplify the average rate so that we can manipulate it more. All right, and we'll do that in the next video.